Alright, welcome to the free body diagram video part 2. For this I'm going to do 9, 11, I'll do 14 for you, and then 15. The rest is yours. Let's start. A 1.70 kilogram block is at rest on a rough incline. At rest means that the net force is 0. 0 newtons all around the block. On a rough incline, the angle of incline is 35 degrees. 35 again. Label the three forces, then break the correct force into its components and label those. Now calculate all the forces on the block, and the friction coefficient is 0.8. So let's start. What do I mean by label the forces? So I have the force of gravity. We have again the force normal equal here. This force normal is equal in magnitude, opposite in direction to the component of gravity that's perpendicular to the surface, or perpendicular to the surface of the ramp. And of course, it's on a rough incline, so that means we have a force of friction. And here, going up, F sub F. Now we are going to break the correct force, so that's the force of gravity. It's not correct because that's what it's called. It's just, I should have rephrased this. We're going to break the weight into its components. So again, one of these components actually gives rise to the normal force, and it's perpendicular to the surface. And then one of these components actually sends the object down the ramp. So remember what the angle is between this green vector, the opposite of the force normal, and the weight is? It's the same as the angle of incline. It's 35 degrees between here and here. So with that in mind, let's calculate the weight first. The weight is equal to the object's mass, 1.70 kilograms, times the acceleration of gravity. The acceleration of gravity is 9.81, so I'll do this in my calculator. 1.70 times 9.81 gives us a weight of 16.67. I'll round that up to 16.7 newtons. And we'll box that in. Now we're going to get the force down the ramp, F down. Or actually, we'll go ahead and get the force normal. So this is a vector. This green vector that I've drawn in just dashed lines is equal and opposite to the force normal. So again, the force normal is the object's weight. In this case, it is 16.7 newtons times cosine of the angle. This is an adjacent vector. Cosine of 35 degrees. 16.7 times cosine of 35 degrees equals 13.6798. So I'll round this up to 13.7 newtons. And my force normal is calculated. Now I'm going to get the force down the ramp. Force down the ramp is also a trig function. It's equal to the weight, the hypotenuse, times sine of the angle, because this is the opposite side. So the weight is 16.7 newtons times sine of 35 degrees. I'll do this in the calculator, 16.7 times sine 35, and I get 9.578. 9.58, I'll round, newtons. And this is equal to F down the ramp. 9.58 is F down. Okay, so now let's get the coefficient of we have the friction coefficient. Okay, this is actually extra information, so we don't need this. Omit this, or else the problem probably won't work out right because I didn't think about that. Ignore that. We don't need the coefficient of friction because we have the force down the ramp. The force of friction is equal in magnitude and opposite in direction to the force down the ramp, and that is because the object is at rest. If it's at rest and I have a force, I'm going to redraw this vector, going up the ramp with the pink vector, and I have a force trying to send it down the ramp, this force down, then the only way that it stays at rest is for these two vectors to cancel each other. So my force of friction then is equal to 9.58 newtons. Okay, going on to number 11. A 14 kilogram block is suspended from two wires. The angle between the wires and the ceiling is 33 degrees, so both of these angles, 33, and same over here, that's 33. Draw and label the forces on the block. Calculate all the forces on the block. So the first force we have is the weight itself, the weight of the object. That is equal to 14 times 9.81. 14 times 9.81 equals 137 newtons. And now we have two strings. Both of these strings exert tension force. So I'll call this T2, this one can be T1. Both of these strings are going to keep the object upright. However, these strings are at an angle. So I need to calculate the vertical components of these angles because they will oppose the weight. Everything is about directions in physics. So this weight is counteracted by the vertical components of tension. These strings make the same angle from the ceiling, and so I will call these Ty and Ty. These Ty's are equal to each other. So if I make a net force equation, I know the object isn't accelerating to the floor. The net force in the vertical direction is 0. Net force in y direction equals 0 newtons because the object isn't falling down. It's not accelerating. So I'll write a net force equation. Ty1 plus Ty2, the vertical component of this, plus the vertical component of tension 2, equals the object's weight, 137 newtons. These two tensions, Ty1 and Ty2, are actually equal to each other because they both make the same angle from the ceiling. So I can say this is like Ty plus Ty equals 137 newtons. Ty plus Ty, x plus x is 2x. In this case, Ty plus Ty is 2Ty. 2Ty equals 137 newtons. So my vertical component of tension is 137 newtons divided by 2 gives me 137 divided by 2, 68.5 newtons for the vertical components of these tension vectors. 68.5. Now just like before, I have a right triangle. This Ty is like the hypotenuse. This T1 is like a hypotenuse. And the Ty is a side, and it has a value of 68.5 newtons. And then I have the ceiling, which I don't need, but I do know that this angle is 33 degrees. I'm looking for the hypotenuse. I have an opposite side, and I have an angle. So this is a sine function again. So sine of 33 degrees is equal to opposite 68.5 newtons divided by the hypotenuse. So sine opposite hypotenuse, and the tension is the hypotenuse. So T1 equals my 68.5 newtons divided by sine of 33 degrees. And this gives me a value for T1 of, let me calculate, 68.5 newtons divided by sine 33 degrees. And I get 125.77, and I'll round that up to 126 newtons. These are the tensions in both strings because they are equal. Okay, next, number 14. A 2.25 kilogram block experiences a static friction force of 15 newtons. So that was nice, given the force of friction equal to 15 newtons. The rope is positioned 34 degrees above the surface. That is 34 degrees above the horizontal. So this is 34 degrees. Determine the minimum pull force needed to overcome the friction. The object is currently at rest. So that means if the object is at rest, this force of friction has to be canceled out by this parallel component of the pull force. This pull force is at an angle. Always, if you have a force that's at an angle, you need to start thinking about how to break that force into a vertical and horizontal component. In this case, I'm concerned about the horizontal component because the horizontal component of this pull force is equal in magnitude, opposite in direction to the force of friction. So this is 15 newtons here for this pull force. That is the horizontal component. That's why the object is not yet moving. And so I'm looking for the minimum total pull force that gives me this 15 Newton vector. So I have an angle, I have an adjacent side to the angle, and we're looking for the hypotenuse. This is a cosine function. So cosine of 34 degrees equals adjacent, which is 15 newtons, divided by the pull force, which is what I'm looking for, F sub P. So I will multiply the F sub P on both sides and divide cosine 34 by both sides. So F sub P, the force of pull, equals 15 newtons divided by cosine 34. This gives me a value of the pull force, 15 divided by cos 34, and I get 18.09. I'll round that up to 18.1 newtons. This is the minimum amount of force you need in order to meet the force of friction, and then once you go slightly above this, you'll overcome it, and the object will start to accelerate. Last one, number 15. A 2 kilogram block and a 3.5 kilogram block are attached by a rope dragged with a force of 6.55 newtons. Find the acceleration of the system and the tension between the blocks. Okay, it looks like there's no friction acting on here. So this is something you'll need to take in account for number 16, and we're at constant speed. All right, so let's do this one. I have 6.55 newtons. We're going to get the acceleration. So F net, since there's no friction acting on here, is mass times acceleration. In this case, the only force acting along the direction of motion is 6.55 newtons. I haven't been considering, the normal force and the force of gravity for these problems because they're equal and opposite. These objects aren't accelerating through the floor, they're not flying up in the air, so right now all I'm worried about are the horizontal forces that actually change the object's motion. So we need the total mass of the system. I'm assuming the string has negligible mass, so I will do the mass of the system is 3.5 kilograms plus 2 kilograms times A, and my net force is 6.55 newtons. So this becomes 6.55 newtons equals 5.50 kilograms times the acceleration. I divide by 5.50 kilograms on both sides, and I get acceleration equals 6.55 divided by 5.50. And the acceleration of the system is 1.19 meters per second squared. I say system and I mean the two block system. So these two blocks are both accelerating at 1.19 meters per second squared. Now there's tension between them. And this tension arises because the 2 kilogram block has to pull the 3.5 kilogram block. this tension is responsible for this single block's acceleration. So this tension equals the mass of this 3.5 kilogram block times the overall acceleration. That is the net force just acting on this one block in the back. So the tension equals 3.50 kilograms, the back block, times the acceleration 1.19, because the back block is still accelerating at this rate. The whole system moves, but the tension arises just because of this back block. Now, if there was no block on the back, there would be no tension because the string would just kind of like dangle on the floor. There'd be nothing. But this tension arises because this mass is accelerating. So this tension then is equal to 3.5 times the acceleration I just calculated. And this is 4.168. I'll round that to 4.17 newtons. Okay, and that's it for this video. Remember to do the rest of these problems. If you need help in tutorials, come find me. Thanks for watching and study well.